All right, so far we've defined the definite integral, now specifically geometrically talking about it being the area underneath the curve. So we are going to actually consider a function or functions defined by g of x going to be the integral from some lower bound a to x of a function f of t dt, or the integral of the f of t dt. So what that's saying is if we have some curve y equals f of t, then our area function is from a up to whatever value x is, from a to b, over some continuous, where f is a continuous function over some a and b. That x value is somewhere in between. So g of 1 would be like the area from a to 1. G of 2 would be the area from a to 2. G of 17 would be from a to 17, or whatever that might be. So the function g depends on x, which is the upper limit of our integral, right there. Now, since the integral represents the area under the curve, we can think about g as being the area under the curve so far, from a up until whatever value for x is. So we're going to take a look at this, and let's see. F is going to be our function shown in below, and I want to evaluate this function g of x, whereas the integral from a to x of f of t dt. So we're going to go through, find values of g of 0, g of 1, 2, 3, 4, and 5, and sketch a graph of that function. Now, thinking about this, g of 0, I'll change that. Our function g of 0 is going to be the integral from 0 to 0. Actually, this should be a 0 there. 0 to 0 of f of t dt. Now, we know that that is the integral over the no space, so that is just going to be 0. G of 1 is going to be the integral from 0 to 1 of f of t dt. So that is going to be the area of that triangle. The area of that triangle, 1/2 base times height, is 1. G of 2 is going to be the integral from 0 to 2, f of t dt. And that's going to be the area continuing. So we've already got the area of 1 plus those next two boxes, up to 3. G of 3 continues that area. Now, this space is about maybe 1.5, because I'm looking, there's almost a full box, and then if we have a little bit extra box, I'm going to say that's about 1.5. So the integral from 0 to 3, f of t, I'm going to add 1.5 because I'm adding that that area with that extra space on the integral. That's going to give us about 4.5. Now at this point, we're below the axis. So up to 4, g of 4, this is going to be a negative space, a negative area because it's below the curve. So our integral from 0 to 4, now I'm viewing that is pretty symmetric to that top part. So that's maybe negative 1.5. Giving us the integral from 0 to 4 of f of t dt is maybe 3. And then lastly, g of 5 would be the integral from 0 to 5 f of t dt. And again, that section is below the curve, below the x-axis, and I'm looking at that, it's about symmetric, so that's maybe another negative 1.5. So we'd be subtracting 1.5 again, giving us a value of that integral about 1.5. So I'm adding that area, plus 1, plus 2, plus 1.5. But then we are subtracting area, negative 1.5, minus 1.5. Let's sketch it. So 0, we've got this point at 0. 1, we have a point at 1. So this is the graph of g of t compared to t. 2, when we get to 3, 1, 2, 3. G of 3 is 4.5, so we're about up there. G of 4 is back to 3, and G of 5 is about 1.5. Now what I look at is our area as we are increasing from 0 to 1, it's getting bigger at a different rate. So from like 0 to 1/2, we're adding a little bit, but from 1/2 to 1, that curve is increasing at a greater rate. So we're going to have something that comes up. As we go from 1 to 2, that's a horizontal line. We are constantly just adding the same amount from 1 to 2. So that's going to be a straight section. From 2 to 3, we're adding a lot, but then we're adding less and less and less. So we're starting off with a steep amount that we're adding, but then it's going to level off. Maybe I'm curving it down. Then we're going from 3 to 4, we're decreasing our value. So we're decreasing it, and I look at it, it's kind of symmetric. From 2 to 3 is the same thing's happening 3 to 4. And then from 4 to 5, we're subtracting, but we're subtracting less and less and less until at this point we're almost subtracting 0. So we'd have something that would look like that. That could be our function g of x. So I'm thinking about how much area are we adding to get to that value. It's kind of neat, doesn't it? So we can find the graph of that curve. do something else. Let's consider that function g of x. Well, what's the derivative of that? So derivative is the slope function. So now we're taking what we just developed here, and we're going to take the derivative, the slope. So I'm going to look at the different parts. At 0, well, we're about 0. And then we are increasing, so small positive, bigger positive, bigger positive. Oh, until we're here. That's really a straight line segment that we had. So from 1 to 2, we're really having just a constant slope there. So we've increased, and then from 1 to 2, we have a constant slope. And if we think about that, that's we're going from 1 to maybe 3, so that looks like it's a slope of 2. Then, all right, from 2 to 3, our slope is positive, but it's decreasing at a smaller rate until, like, ooh, there, our slope is 0. So from 2 to 3, our slope is decreasing until we get to 0. Oops, why did that straighten line? So decreasing, and then we have like a slope of 0. From 3 to 4, it's slightly negative, but then it's more negative. So, and at 4, then it's still negative, but oh, it's getting a little bit less negative until about 5. It's at about 0. So 3 to 4, we're more and more negative until 4 is like the greatest negative bit. Then from 4 to 5, it's being less and less negative. Why is that straightening out? So there's what the derivative would look like, thinking about sketching the curve along the way. Huh, that looks kind of familiar. So the derivative, so this was the integral from 0 to x of f of t dt. That was g of x. Now this is g prime of x. That's the derivative, but g prime of x, if we go back, that looks awfully a lot like our function f. So it looks like g prime of x is actually equal to f of x. Huh, we went from the derivative, from the integral down to just f of x, which is that plugged in there. Curious. The derivative and the integral are going to be related. Now, that's what we're trying to see here. Derivative and the integral are going to be related. Let's generalize a little bit. Walk out that bottom part. We can say that g of x plus h minus g of x is approximately equal to h multiplied by f of x. Now let's think about that in context. So I'm coming over here to the right. G of x plus h is going to be from 0 to x plus h of f of t dt. Now g of x plus h is out of that area. G of x is going to be the integral from 0 to x of f of t dt. So the subtraction between those two would be the difference between those two integrals. Well, it's that area all the way to x plus h, subtract the area that came before x. So that leaves us with just this single rectangle where the width of that, the base is h, the height is that f of x. So that difference between the integrals is actually, okay, there's our base times height, one single rectangle. Now manipulating that, if I divide by h, turns it into g of x plus h minus g of x all over h, is approximately equal to just that height. But that looks kind of familiar. At a limit, as that h gets smaller and smaller and smaller, that gets closer and closer to just the single height of that. But that's the definition of the derivative. So g prime of x is actually equal to the value of our function with that value, the upper limit x, substituted in. Oh, but g of x is the integral from sum a to x of f of t dt. Then the derivative, look at this, the derivative is just that x plugged into our function. Look at that. The derivative of the integral is just the argument, the integrand. What we have here is called the first fundamental theorem of calculus, the fundamental theorem of calculus part 1. When f is some continuous function on AB, then the function g defined as that integral from a to x, where x is something in between a and b, that is continuous on a and b and differentiable on a and b. On the the open interval AB, then the derivative of g is equal to just the integrand evaluated at x. The derivative of the integral is the integrand. So the derivative of the integral is the part inside the integral. Derivative cancels the integral. So let's see this. Let's try this out. What this is telling us is if we have the function g of x is the integral from 0 to x, the square root of 1 plus t squared dt, find the derivative. By the fundamental theorem of calculus part 1, g prime is going to be the integrand, or inside the integral, evaluated at x. So g prime is going to be the square root of 1 plus x squared. That's it. The derivative of the integral is the integrand evaluated at that upper limit variable. That's all. Next up, different function, s of x, is defined as this integral from 0 to x of sine pi t squared over 2. The derivative. Oh no, look, that's crazy. Nope. The derivative of the integral is the integrand evaluated at that upper variable. So s prime of x is going to be equal to sine of pi x squared over 2. Done. That's it. The derivative of the integral is the integrand evaluated at that upper limit. I'm going to change things up a little bit, though. Let's take d dx, so the derivative of the integral from 0 to x to the fourth of secant t dt. Now here, our upper limit, x to the fourth, we've got something more than just x here. Now, let's think about this. I'm going to replace this and put a u in play instead. So we're going to take d dx of the integral from 0 to u of secant t dt. Well, that tells us then that we're going to have secant of u evaluated, the integrand, the inside the integral, evaluated the upper bound. But d dx of u, we need to remember the chain rule. So this is going to be multiplied by du dx. So I made the substitution that u is x to the fourth. Then du dx, chain rule, is going to be 4x cubed. So this is actually, I'm going to write the whole thing, the integral from 0 to x4 of secant of t dt. It's actually, okay, that derivative, 4x cubed multiplied by secant x to the fourth, chain rule. Notice this is not the derivative of secant. We are not taking the derivative of secant. All right, one last example. I'm going to step it up quite a bit and see this in an application. So here we've got this function, this graph of some function f. It is a continuous function on this closed interval from -4 to 6. The graph of f consists of 4 line segments as shown. We could write a piecewise function for that, but I don't care. G is the function where g is defined as the integral from 0 to x of f of t dt. First, on what open intervals of g is the graph g concave up? So what I'm thinking for A, g is concave up when the second derivative is going to be greater than 0. So we need to find the second derivative. We know that g of x is 0 to x of f of t dt. So the first derivative, g prime of x, is going to be, applying the fundamental theorem of calculus part 1, f of x. All right, well, there's the first derivative. Our second derivative, g prime prime, then, the derivative of the derivative is that, the derivative of the derivative. So we're looking for f prime of x. So concave up, we need f prime of x to be greater than 0. If we go back and look at that graph, I'm going to take an interval, we look back at that graph, I'm going to do my work up here. F prime of x from -4 to -2, our slope is positive. From -2 to 0, our slope is negative. From 0 to 2, our slope is negative. And from 2 to 6, our slope is again positive. Ooh. So we wanted when is g concave up, so that's when f prime is positive, so from -4 to -2, and from 2 to 6. The justification, give a reason for your answer, that's the sign chart. So we've got from -4 to -2, from 2 to 6. Second question that we have is let p be some new function defined as g of x multiplied by f of x. We want to find p prime of 3. Well, first, I'm going to go through and find the derivative of p. Ooh, product rule. That's going to be g prime of x multiplied by f of x. Add to that g of x multiplied by f prime of x. Now we know that g prime is f of x. So we've got f of x multiplied by f of x. G of x is that integral from 0 to x of f of t dt multiplied by f prime of x. So I have everything in terms of that graph f. We want p prime of 3. P prime of 3 is going to be f of 3 squared plus the integral from 0 to 3 of f of t dt. Notice that's going to be the area under the curve multiplied by f prime of 3. So let's take those values. First off, f of 3. F of 3, there's 3, 1, 2, negative 3. So it's going to be negative 3 squared plus the integral from 0 to 3. So that's going to be the area from 0 to 3. Now what I see is, in here, that's positive, that's negative. So the integral from 0 to 2 of f of t dt is going to be 0, because that cancels with that. Then from 2 to 3, all right, we've got 1, 2, 3 and a half. That's going to be 3 and a half. That's 3.5 multiplied by f prime of 3. So f prime of 3, we want the slope. F prime of 3, that looks like the slope of 1. So that's going to be 1. We've got 9 plus 3 and a half gets us 12.5. Not too shabby. Last one, letter C, we want this limit as x approaches 2 of g of x over x squared minus 2x. Now we just saw that the integral from 0 to 2 of f of t dt was 0. Ooh, thinking back to that, from 0 to 2, that cancels with that. That integral is 0. This is going to give us 0 over 0. Oh, L'Hopital's rule. So then we've got the limit as x approaches 2 of f of x, because f of x is the derivative of g of x, over 2x subtract 2. Now, f of 2, we can see f of 2 is negative 4. 2 times 2 minus 2 is 2. We've got negative 2. There we go.